So let me just spend a moment sort of looking at an analysis. The goal here is to sort of give you sort of a sense of the mathematics without, this is not meant to be sort of a rigorous sketch of a proof or something. Okay. So what I want to do is to sort of see if I can sort of come up with a mathematical model for this output voltage, assuming that I've started my little bistable system near this thing. So what I want to do is build a mathematical model of how this voltage changes with time. The first thing I'm going to do is to come up with a probability that I'm actually stuck in this state. So this problem only happens for a sort of certain combination of timing of the D and the clock signals in our flip-flop. And this is a picture of the voltage on this feedback node, which often is perfectly legit, but there's a moment in which it's changing. So depending on how close to the middle I want to get, I can sort of make this sort of analysis that has to do with the entire clock period. In other words, how long the clock period is. What this window of the window of stability has to be, so that sort of gives me a region that I'm particularly sensitive to when I'm going to actually have a chance of putting that feedback loop into a metastable state. And it has to do with how wide that region sort of is, right? So I'm really trying to compute the area of that little rectangle in there, sort of as a percentage of, how big the percentage of time that I'm actually in this window and the percentage of time I'm likely to actually be as I transition from a digital 0 to a digital 1. What percentage of time am I actually likely to be in this middle range? And you can come up with some, this is just, there's 1,000 formulas you can have. This is just trying to come up with some estimate of the chances I'll be in this little gray rectangle, which is this time that I'm really worried about. That's when I have a chance of being in the metastable state, as relative to the length of the clock cycle and the length of the transition from 0 to 1, the number of volts I have to go across. Okay, so this is just an attempt to say, look, the chances of me actually putting my system here in the metastable state, okay, has to do with how long the clock period is relative to what the setup and hold times are, and then how far apart the voltages, the high and low voltages are. So as I make the clock period longer and I make my voltages higher and higher, the voltage difference between 0 and 1 higher and higher and higher, the chances of actually being at this magic point as a function of time, sort of go down. Okay. So the details here don't really matter. I'm just trying to put some concrete something down that sort of gives you a sense of the argument I'm trying to make. Now what I'm going to do is to think of this guy as an amplifier, my little positive feedback loop as an amplifier with a certain amount of gain. And I'm going to sort of try to write some classic equations for, I have this little RC thing that I'm charging up or discharging. And I can write equations for those voltages. What you can do is that the idea is that if you keep applying gain to something, a constant amount of gain to something, its value changes exponentially with time. Because it grows a little bit, but then you apply the gain to that, and so it grows not linearly, but exponentially, because the gain keeps getting applied to itself again and again and again. So there's these sort of positive feedback loops. I get this sort of exponential graph of what the voltage looks like. So if I made a graph of what I expected the voltage to look like over time for this particular node here, I might see something where I'm very close to, this is going to be the middle point, like so. And I might expect to find the voltage sort of growing exponentially this way or exponentially that way. Okay. And here's the insight. You can say exponentials, boy, Chris, I don't have to wait very long for exponential amplification to change something from a very small value to a very large value. That's what it means to grow exponentially. These curves get huge really quickly. On the other hand, if you say, look, you have to reach this value or that value, so you have to reach V input high or V input low, and you have to do it by a certain bounded time t, okay, the argument I want to make is that I can play devil's advocate. Even though you have exponential amplification working for you, I can pick a point that's close enough to that balance point, okay, that in that time you won't have reached a legitimate digital value. Even though it's busily changing, and in fact it's changing exponentially with time, the point, you apply exponential amplification to a small enough value, it doesn't make it big instantly, it takes a certain amount of time. I have to wait for long enough. And if you give me a bounded amount of time I have to wait, okay, I can come up with a placement of that middle voltage that's so close that I won't have achieved either a digital 0 or a digital 1 in the time that you give me. Okay. So, we can come up with some formulas here, but the idea is that there's this exponential time constant involved.